worked on applied algebraic geometry, computer science, and statistics and stuff like that. I've been working on compiler to put zero knowledge proofs, to turn machine learning models into zero knowledge proofs, and sort of generally work with ZK in the past year, which is called zkiap. I met some of the folks in East Denver where we built some stuff with that. So I'm not, I'm becoming an expert, but there are many people more expert than me in ZK. So there may be some questions I don't have answers to, but I'll try to get back to you if that's the case.
Wow, cool, great. Thank you, Justin Martin. And so let's start our office hour. Now, can the host mute their iPhone? Okay. Let's continue. This week we started session 6 and session 8.
谁那边没有静音，麻烦静音一下。那个或者 Damian， 我的 host 权限已经移交给你了，然后你把那边静音一下。
Okay, cool. So, okay, let's continue. And this week we started the ZKIP sessions, session 6 and session 8, and everyone's question has been compiled into a list and sent it to Justin Martin. So now we can look at these questions and invite Justin Martin to answer it. So how about let's start with question 1.
Okay, so this is the question about, is this the question that you sent me, the selecting S and T, this kind of stuff?
Yeah, it should list on in the email, maybe. I don't know if you have received
just now, or not sure I haven't. Do you want to just read me the first one to see if it's the same what I think I have? What's the first question?
Yeah, the first question is about the select S and T efficient multi-exponentiation.
Okay. Yeah, so that one is kind of in the MSM algorithm, or in the Peppinger algorithm. It works for any value of those, and this is kind of chosen to make the calculation at the end work out for the complexity. So you could make other choices, but I think probably those are the ones that are written in the session, which are, let me just pull it up. So we started out just saying, okay, S and T or something, and then I think we want to get to a certain complexity for the whole calculation. So it sort of turns out that taking S to be square root of lambda over n and T to be square root of lambda n is basically an optimal choice, or there's some kind of trade-off that happens in the efficiency. And with that choice, that just kind of makes the math work out nicely. So not super magical, and there might be a kind of individual situations where it makes sense to change those because it sort of changes your leg size, word size. And so depending on the characteristics of the computational platform, it might make sense to adjust those. Or the problem in terms of how it trades off between kind of the length and width of the computation. Yeah, so I'm not sure I have much more to say about it than that. Let's look at the next one, maybe. So Yeah, so KZG commitment, for example. So in computing a KZG commitment, you are computing a multiscalar multiplication, right? Because you have a bunch of values, each of which represent a power of tau times a group element, and you only know the result of that, right? G to the tau to the whatever. And we have the structured reference string, the shared reference string that everyone gets. And so from the point of view of computing that polynomial commitment, all we're doing is saying, I have a polynomial, it has a bunch of coefficients, each of which is in the field, and I'm taking each of those coefficients in the field, multiplying it by the point, the elliptic curve point represented by the pre-computed G in the structured reference string, and then I'm adding those all together. And so that's an MSM. So the computation of the commitment to a column or in a Planck or Hilo 2 or whatever a KZG involves an MSM. That's one of the more expensive parts of the, or we pay a cost every time we do that. So that's probably the best example. So the bilinear part is in the check when we're checking that the commitment is accurate. So the check is relatively cheap, but the creating that commitment is where we pay the MSM cost. And it's not different groups, it's different elements of the same group. So when we're computing the polynomial, each element of the same group, G1, G2, G3, the role that's, or so in the MSM, it's just like a general sum of PI G1 plus P2 G2 plus P3 G3 plus blah, blah, blah. What are the G's in this case? In the KZG case, the G's are elliptic curve points that come from a trusted setup ceremony. So you get from the trusted setup a long list of those points, and those are the ones you're using in that calculation. That makes sense.
So does everyone has some questions about it? Okay, if there is no question, we can go on with question 2.
Or so that was question 2, the one I just was talking about. Next one would be 3, I think. So this is G1, G2 up to GI, and Peppinger generators from the same graph. So they're points on the same curve. For example, the points that were given from the SRS. So so the product, the sum of products is what we mean by we say we evaluate the polynomial on that curve. And then maybe someone could tell me question 4. Is that?
Oh, I put the question 4 in
There we go.
the.
Here's a question. Why is it necessary to assume that lambda is greater than or equal to n? The Peppinger paper. That I have to think about for a minute. Okay, so what is lambda again? Let's remember.
Lambda is the of the length of E to power of lambda.
Okay, so we're saying okay, so lambda is the number of bits of the prime. Oh, right. Okay, so this is because what we're doing here is we're breaking it, right? We're breaking lambda, we're kind of breaking the space up into legs, just like we would, if we were doing a computation with 256-bit integers, we might break it up into 4 places, each of which are 64-bit integers. So just a place value decomposition. So then why is it important that lambda is greater than n. I think if lambda was less than n, it wouldn't make sense to break that up. Like in order to be able to break it up into legs, then the maximum value you can ever have in that prime field is lambda, or 2 to the lambda, basically. So if you were in a situation where n was smaller than lambda, basically you would have one leg. So s would be 1 and t would be lambda, or yeah. And so that would be like a collapse of the Peppinger algorithm into sort of a one-dimensional version. Okay, let me try to check out this discussion from the GitHub. Oh, wow. The picture of the board with my bad handwriting. Okay, you have to help me. Unfortunately, I don't have any. Actually, I could try Google Translate. So for the next question, if anyone wants to.
Oh, I wrote it in the box. It's an NTT problem.
H+H NTT problem. Yeah, so why are we choosing roots of unity? Let me think about how to say this. So we also make the same choice of roots of unity when we're doing a Fourier transform in the complex domain, like using complex numbers. And so, okay, so the not very helpful answer is that the trick that we're using, the Fourier transform trick, kind of depends on roots of unity to operate. And I think we didn't in this lecture detail how exactly this Fourier transform trick works. But you can think about it, or so one way to think about it is to say the Fourier transform as represented here is a linear transformation from the coefficient basis to the evaluation basis, or the evaluation to the coefficient basis of the polynomials. And the matrix of that linear transformation, linear transformation is a linear map. It goes from one thing to the next. That goes from coefficient basis to and back. And the matrix of that linear transformation is a van der Waals matrix. And that van der Waals matrix is expressed in terms of the roots of unity. So if we used a different number as the evaluation point, we would still get a matrix, but the matrix would not have as nice a form. And we wouldn't have this efficient algorithm to apply the matrix, because we're not applying the matrix in the literal sense by doing matrix multiplication. We're applying the matrix using a recursive algorithm. Yeah, so it'd be instructive to try for a small example, write it out with not the roots of unity, and see what matrix you get, and then ask yourself, how would you compute the transformation represented by that matrix in a more efficient way than just doing the dot products. So we get to do, instead of n squared, we get to do n log n field operations. I'm trying to think of a good intuition as to why that's going on. Yeah. I'll see if I can think of something maybe and send it over after the call. I don't have a good idea for why, other than to say we just don't have this nice algorithm without without the roots of unity. In fact, there's other algorithms for integer multiplication in places where we don't have roots of unity, and they kind of fake the roots of unity. They sort of construct roots of unity in order to do it. So then the next question perhaps is this.
Oh, that's all questions now. It's the last one, so.
Oh, that's the last one. Okay. There was a couple of questions linked, and I just couldn't quite parse them. But that question 5. Okay? So you know about the binary. It's already kind of binary. Yeah. You have the last 2 figured out. Okay. All right. So I will think about how to give you a good intuition for what's going on with the Fourier transform. Is a little bit magic, for sure. And the question of what is special about the property, what is special about roots of unity that make it possible, is a good question, because that's certainly an awkward thing. It's neat because in something like the Halo 2 system, we really get 2 benefits from the roots of unity, which is that we get the fast Fourier transform, but we also get this ability to do kind of rotations, which allows us to express a computation in fewer gates at the cost of using these rotation evaluations, and that's quite nice. So there's a double benefit.
So maybe anyone has some questions wants to ask? You can just ask it. Yeah, and type your message here to send it.
对，就是可以直接上来用中文问也可以，或者是打在聊天框里都可以。
对，可以让安努的帮你翻译一下。
Hi, H+H Mortan. Maybe we can give several minutes to our students, and they can maybe ask questions either in Chinese or English, or type the questions in the chat box.
Hi, Jason. I have a question. So just now you mentioned you have been doing the ZK in machine learning for the past year. So I'm wondering what's the benefit of using ZK in machine learning?
Yeah, I mean, the quick explanation for it is that so ZK in general, right, is, I like to think of ZK as being, you either replace digital signature algorithm where I have a private input, a public input, which is the hash of the message, and I have a public output, which is the signature. And the algorithm I run is something very simple, like in BLS, just raising it to a power, right? Raising the hash of the message to the power of the secret key to produce a signature. And then what zero knowledge proofs let us do, and so that's an digital signature is an example of a zero knowledge proof, and it can be checked on chain, if you're interested in doing it on chain, or it can be otherwise easily checked by a verifier. And then what zero knowledge proofs do is let us put in the algorithm we like inside that box instead of the signature algorithm. And so by putting a machine learning algorithm in it, it means that I can run a machine learning model and you can trust that I ran that model. And that's interesting because in the blockchain setting, it lets us run machine learning models as though they have run on chain. In other words, it's like, it gives kind of eyes to a blockchain, Ethereum or whatever can see what happened in the world because it knows how to process images. It's as though the model was running on chain. And that also lets it kind of make judgments about fuzzy things that have happened instead of just sort of black and white judgments about did this contract execute the way I expected it to. It's also interesting in other settings where you don't have a blockchain, so something like you want someone has a machine learning model that's sensitive for some reason. For example, it's used to screen resumes, screen CVs, and you want to show that it's behaving in a fair way. So you could prove that the execution of that algorithm is fair against some test set. And then anyone who receives the output of the algorithm, the Java applicant, can check that it was indeed fair. So things like that, you could use for some privacy-preserving medical stuff. It can also be used for kind of provenance of things that go through transformations, like you have a camera that takes a picture, the image is signed by the camera, and then you apply some transformations to that image, making everyone look better or whatever, right? Removing things you don't want in the picture. And then you can prove that the transformations you did to the image didn't change the content, just adjusted the colors or whatever. That's another example.
Got it. Thank you.
Hi, Jason. I also have a question. That last office hour we discussed already, but we are not sure is that correct answer is the B's value in that Peppinger paper. I don't know if I pronounce right. There is a B value to split that. Let me check that paper. Is the section 3 to split that.
This is the Boodle paper, Jonathan Boodle, efficient multi-exponentiation. Is that what you're referring to? Or
yeah.
Okay. Yeah. So yeah, in this one, right. So
yeah,
B let be some parameter to determine later. That one.
Okay. I think let me finish my question. During that time there is a T0 for a side to compute all the combinations for that possible multi products or all the elements. So my question is why compute all that possible products since we only need one product, right?
No, it's more like you're going to need, so the final product will be assembled from these blocks, from elements of these things. And okay, so suppose I'm computing some abstract syntax tree, or I'm computing some polynomial. There's a trade-off between kind of memory and number of steps, which comes from, I take the whole polynomial. If I don't do any blocking and I just compute everything as I go up the tree, then I've done a lot of steps, but I haven't used excess memory. I could even just use like one register that can hold the current value and kind of accumulate it all up. Then if I do this thing, what it's saying is that I expect to see many sub-expressions repeated in this big tree. And so this blocking strategy, the T's, is basically an attempt to compute sub-expressions that we expect to see. So we pre-compute some sub-expressions and then we reuse those sub-expressions, and that reduces the overall number of computations. And it's a worst case algorithm. So in other words, we're trying to prove the performance in the worst case, like a normal complexity theory thing. So it doesn't, it has to make choices that will work for every possible input. And so it's not being smart about choosing only sub-expressions that appear. Instead, it's computing all sub-expressions of a certain size, basically.
Okay, so this preset can reuse for different scenarios or different algorithms, or it's just for one problem have one this.
So what I'm saying is that this is an algorithm that says, okay, I ahead of time I don't know what my coefficients p are going to be in the polynomial. Right. So for example, if it was a sparse polynomial, I don't see it. So I expect that they're going to be dense. I have no control over what they are, and I want to come up with an algorithm that will efficiently handle any situation that you throw at me. And so in order to do that, I have to assume that basically all these sub-expressions are going to show up. And that's why it's computing kind of all possible sub-expressions, or grouping them and computing sub-expressions for chunks, and then combining those sub-expressions. If I knew in advance that some elements of the polynomial would be 0, I might be able to skip some of these multi-products in the set T.
Okay, I see. Yeah. Regarding 0, it reminded me there's another question for that 0 issue is in this paper in the beginning there is a binary expand and the G's value equals to the each of the binary values in that position. And it's just it seems that this equation just compute from 0 to lambda. Actually, some value don't need to compute or don't need to go there's so many values from 0 to lambda. And maybe some, for example, if that value is 7, is only have 3 digits, right? But lambda is a large number. We don't go to that large number. So in practice, is there the algorithm just check the digits and will not go to compute, or is there any way to do this? I don't know. Is that clear for my question?
Sorry, I don't think I quite understood. Yeah.
Okay.
So the EIs are the exponents, right? In the algorithm.
Yeah. The ES EIL, the EIL's value, the IL's range is from 0 to lambda equals to 1. Lambda subtract 1. But some IL's value is suppose lambda is 1 million, and actually for some EI's value, for example, EI is 7, then actually L's next value is 3, right?
Well, so is there a particular spot that you're looking, or so one thing is, of course, lambda is basically the number of bits of the prime. So a 1 million bit prime would be very unusual.
Okay, I think maybe later I can read to the text and send it to you.
Okay, sure. Yeah, probably this sort of thing is always easier to do when you can write the.
I think so. Okay, because this Zoom is a personal account, so we have just four minutes left, and maybe we can just take one last question. So anyone who wanted to ask their last question?
Hello, Morten. I'm wondering, is there any specific protocol for doing inference for deep learning models, or less general protocols for doing this task?
Yeah, good question. So there's been a lot of specific protocols that have been written over the years for doing deep learning in zero knowledge, and in some sense, you always end up doing that. The approach that we've been taking is to use Halo 2, which is this well-known package for doing deep learning or doing ZK proofs, and make it work inside of that package, partly because it makes it easier. You know, someone else is maintaining a lot of the upstream stuff and making sure that the system is secure, and also helps with interoperability with other gadgets. So if someone makes a signature checker or something, then it's easy to plug it in with the rest of the model. So yeah, and so that'll be a constant tension of like custom systems, less custom systems, things that plug into other proof systems. I think it's really interesting to think. I'm of the opinion that all kinds of composability are going to be really important in ZK. So systems that are maximally compatible with other work that people have done and other ways of doing proofs will kind of agglomerate, right? Just like in any software ecosystem, the more compatible it is, the more packages you have, the more you can do. There's sort of a combinatorial explosion of possibilities. And so I'm a fan of systems which are, if they're customized, the customization is kind of internal and it still can plug in with everything else.
Yeah, gotcha. Thank you.
Okay, well, thank you so much for your interest. I hope I was at least slightly helpful, and feel free to ask me other questions offline.
Okay, that's all questions for today. So thanks very much for Professor Jason Martin for his patience in answering our questions. So maybe there is some language barrier between us, and we need to watch replays later to re-understand this. So okay, thanks very much. So Auspice hour is over. So thanks for everyone to attend to it. So we can say goodbye to Mr. Jason Martin. Thank you.
Thank you. Bye.
Jason, bye-bye.